Hey everyone, I hope you are doing well. Yeah, for some reason people are not watching the videos, so I hope these videos are useful for you. But I don't know. At the end, it depends on you whether you're going to watch the video or not. Because you already know that you can change the grading scheme to pass and fail, which is pretty helpful. You don't have to worry about the grades anymore. But if you are worrying about the grades or you want to do better, I would suggest you go through the videos. So yeah, let's get started. The topic we're going to focus on today is the bitwise operations. So bitwise operation basically means the manipulation of bits. In the previous lecture, you have noticed that everything in computers are just basically zeros and ones, which are bits, right? Bits consist of like two digits, 0 and 1. And today we are going to just learn how to work with them, and we will also learn um, how to do the manipulation, and it's going to help you in your assignment CO7, which is also uploaded recently. I'm making this video as early as possible so that you can start working on it as early as possible, because you don't wanna spend too much time on that and wanna put more time on the GIS assignment. So yeah, let's get started. Bitwise operations. C includes operators that permit working with bit level representation of a value. Well, C allows that. I think Java allows that a little bit, but I cannot think of other languages that actually give direct power over like bitwise, but there might be some. I didn't try it. So in like for bitwise manipulation in C, you can do like left shifting. You can do shifting to like left and right. You can do complement. You can do and, or, XOR, and so on. And remember, this is the representation we go with. The lower bits are going to be at the top right, at the most right, and the higher bits are going to be at the most left. So this is the normal representation of bits, and this is something you'll be working with. Indianness. I mentioned in the class briefly in one of the classes, like what is Indian. So now we will be learning about them formally. So when a multi-byte value like int32t is stored in the memory, there are options for deciding how to organize the bytes physically. For example, this numbers byte representation is like this, and as it is like 32, there's going to be 32 digits of zeros and ones. Now the question is, how are they stored in the address? So over here we just made them like put them normally like left to right, with byte corresponding to the highest powers of 2 on the left and the byte corresponding to the lowest powers are on the right. Like this is the highest one, this is the lowest one. It kind of makes sense, right? But in memory, there's no left and right. The memory is kind of like a block. Now it depends on how you're going to store stuff in the memory. Instead, each byte is stored in a specific address on the memory. So int32t value will occupy 4 consecutive 4, because 4 into 8 equal to 32, right? Consecutive address. So it depends on like how are we going to put them, because like it could be the higher numbers could be over here or over here. Now at the end of the day, you have to figure out how they, well, you don't actually need that, but this is something you need to know. And it was also a case in CO5. Like if you try to print something in CO5, you would have seen that they were acting differently. Like for example, if something was supposed to be like this, it would print something like this. The main reason is because of Indianness, and today it might make more sense. So what C actually uses is x86 system, and it uses the little endian byte ordering. So what is a little endian byte ordering? So in this representation, just like the previous slide, so what we're going to do in case of like C, as it uses little endian system, the high byte order is stored at the high address and low order byte is stored at the low address. So this was this part, right? So as you can see, the higher part is put near the high address and the lower part is stored in the low address. So this is a normal representation in x86. Note that the bits within a bytes are always stored in little endian order, high order bit first. That's pretty straightforward. Like there's no difference in the byte, they are stored side by side, but the difference is how the bytes themselves are stored. So the higher bytes are near the high address and the lower bytes are near the low address. So if you have some number like this, a 0 1, like I meant 1 0, like I mentioned before, and if you try to print it, this one is going to be printed first because it's in the lower address, and then it's going to be printed. And remember, in JVM, like if you're using Java, it uses big endian byte ordering. So this is one of the biggest difference you will see in x86 and JVM. So if you try to manipulate bytes directly in C and Java, the code is not going to give you maybe the output you are expecting. So in most situations, you don't have to order about the whole byte ordering on your system because the compiler itself takes care of it. Like you don't have to worry about how the bytes are stored and anything like that, because um, like realistically speaking, you will never be working on that low level, but like that's something you should know about, like for your job interview or anything like that. So in that case, you should know which one is like little endian and which one is big endian. And honestly, I still make these mistakes. So if you still make these mistakes, it's fine, just Google it or something like that. But yeah, this is something you should know about. Like they are very system specific and the compiler takes care of it. If you ever do memory dump, like hex dump or something like that of a binary file, and if you try to examine it by using pointers, you have to know how they are, which orientation they are in. When are you going to do hex dump? Well, when you're trying to hack something. So in terms of like hacking or anything like that, if you want to do those stuff, you have to know how the orders work. Like if it's x86, it's going to be little endian. If it's JVM, it's going to be big endian. So when you're trying to do something like this, you have to know which one you are working with. And another thing is, like if you transfer some like binary files created on a system using one byte ordering to a system using an opposite byte ordering, you'll have to compensate for that. So like for example, you like the standard isn't always maintained, but like it's taken care of by the compiler. But there might be a case where you're like copying one type of byte ordering and copying it to somewhere else. In that case, you have to compensate for it. So yeah, that's something you should be aware of. So let's get started with the bitwise operands. The first one we're going to work with is bitwise shift. So we have the right shift and the left shift. So how do they work? So basically what um, this one left shift does is it basically shifts the bit on the left. This is the number that's going to be shifted, and this is number of bits that are going to be shifted. Again, it's same for the right shift. This is the number that is going to be shifted, and this is the number of bits that are going to be shifted. It will make more sense soon enough. So the bits of EL are shifted ER positions to the left. In this case, zeros will fill the vacated position on the right. The resulting value is returned. Okay, and in this case, if EL is unsigned or signed and non-negative, return value of the integer EL is going to be this. Sorry, the integer is going to be this. Is going to be divided by 2 to the power this. If EL is signed or negative, the result is implementation dependent. Like, it depends on the compiler itself. So here's an example, and I think it will make more sense of what I just mentioned in the previous slide. So we have two numbers, x and y, right? And if we try to do a left shift by 5 on x, what's going to happen is the bits are going to be shifted by 5. So over here, 1 was here, and over here you can see that 1, 2, 3, 4, 5, and it's over here. So this one was shifted by 5, then the 0, then the 1, then 1, 1, 1, 1, and so on. I think that makes sense. Like, I probably don't have to go more about it. So that's one thing. The other one is right shift, right? So in this case, the numbers are going to be shifted on the right side. So in this case, by 5. So 1, 2, 3, 4, 5. So this one is going to be here. This one is going to be here. This one is going to be here. Sorry, I missed a position. This one is going to be here, and then there's 0, and so on. So as you can see, some of the digits, like 5 digits over here, are going to get lost. So when you're doing a right shift, if it's a signed number, in this case they are signed, right? There's no U over here. In that case, it's just going to be append, like in right shift, it's just going to be padded by zeros. And if it had 1 over here like this, it's going to be padded by 1. Even in this case, it's not padded by 1, it's just padded by zeros. There's no padding in this case, my bad. So yeah, and whenever you're doing a left shift, these parts are going to be filled in with 0. If you're doing right shift, it depends on whether you have 1 or 0 over here. If it's 0, then it's going to be padded by 0. If it's 1, it's going to be padded by 1. Let's see what happens for a negative number. So if you try to left shift it, in this case, as you can see, this is the number, right? If you shift it by 10, there's going to be 10 zeros, and then you see the number that was there before. And if you try to right shift it, as you can see, by 4, it's going to be right shifted by 4. So these 4 digits are going to be lost, and over here, as you can see, they are padded by 1. So what happens in case of UN32? Well, you can give it a try by yourself. So remember in the previous slides we mentioned that it is kinda implementation dependent. So in this case, you can see that if we did left shift, it's going to be a multiplied by 2 to the power 5. Why that happens will show soon enough. And if we do right shift, it's going to be divided by 2 to the power 5. If we do left shift, it's going to be multiplied by 2 to the power 10. but in this case it's not the same. Why does that happen? Try to figure it out. Take it as a homework or something like that. So anyway, we have seen like left shift and right shift. Then next one we're going to take a look at is logical negation. So if you did discrete math before, I think it will make more sense. Like if x is 0, if you do a complement, it's going to be 1. If x is 1, the complement of x is going to be 0. It's pretty straightforward. But in terms of complement in C, what it's going to do is change the whole number. So for example, in my case, like I have a number like this, 0 0 0 1 1 0 1 0, something like this. If I do a complement of it, it's going to switch all the bits. So in this case there's 0, so it's going to be 1. This one is going to be 1 1 0 0 1 0 1. So how you can look at the operand complement or negation is the whole thing is going to be switched. It's not like this, because in this case what's going to happen is, if this is my x, if I do something like this, it's just going to be zeros. Remember, this negation, this is not negation, is basically I forgot the term for it. I'll take a look at it later. So in this case, this is a Boolean operation, right? A not operation. In this case, what it's going to do is, if it's true, it's going to turn it into false. If it's false, it's going to turn it into true. But this one basically switches all the bits. So this and this are not the same. There's also the logical AND operation and OR operation. So in this case, 0 0, remember, if there's any sort of 0, it's going to be 0 in terms of AND. If there's any sort of 1, it's going to be 1 in terms of Y. So how the bitwise operation in C works is, for example, I have something like A equal to 0 0 1 1, B equal to 1 0 1 0. So if I do something like A and B, what's going to happen is it's going to match them one by one. So the first number is 0 and 1. As we can see over here, it's going to be a 0. 0 0, obviously that's going to be a 0. Then 1 1, we can see over here 1 1 is 1. And then 1 0 1 0, which is 0. So if we do A and B, this is what we're going to get. And if we are going to do A or B, what we're going to get is, remember, if there is any 1, it's going to be 1. 0 1, so it's going to be 1. Oops. In case of 0 0, it's going to be 0. 1 1. So this is the output. So this is how and or or and works in C. So yeah, I hope that makes sense. So there's another one, which is XOR. What XOR does is, if they are opposite to each other, it's going to be 1. If they are same as each other, it's going to be 0. So if I have another example, if I have like 1 0 1 0 and B is like 1 1 0 0, what XOR is going to do is, they're the same, 0. They're the opposite 1, same 0. Another thing to point out is the XOR operand looks like this in C. This is not to the power of like what you usually use. The caret in C works like this. Another thing I forgot to mention, the AND operand is an ampersand, and this operand is the or. The ampersand is and, this is or. And remember, if it's like this, it's an AND operation, but if it's something like this, it's an address. I don't know when they were making the compiler why they use the same symbol, but yeah, this is how it is. Get used to it. So yeah, so let's see something called bit mask. So a C programmer uses something called mask when they are working with bitwise operations, and it's just to make someone's life harder, honestly. Like you can use bitwise operation because they are super fast. Like you can imagine how fast they are, and any other operations are pretty slow. And you will see that case of division. But anyway, so if you claim to be a programmer, you have to know how to do bitwise operation, because many of the C programs are written in bitwise just to show that, like literally just to flex on others. So yeah, let's see what masks are all about. So this function is trying to see if a number is a multiple of 4. This is the parameter, this is the number we are going to check. So we are going to make a mask which is 0 0 0 0 0 0 0 3. Over here there's a OX, which means that this is a hexadecimal number, and it looks something like this. So one thing to know about binary numbers is, if it's a multiple of 2, there's going to be 1 0 at the end, and it can be whatever it wants. This is multiple of 2. If it is a multiple of 4, there's going to be 2 zeros at the end, and so on. So multiple of 4. If it's a multiple of 8, there's going to be 3 zeros at the end. If it's a multiple of 16, there's going to be 4 zeros at the end. I hope that makes sense. So in this case, if we want to check whether a number is a multiple of 4, we need to check the first 2 digits, right? Because if they are zeros, we know that that number is a multiple of 4. So in this case, we are getting a mask which takes care of the first 2 digits, and everything is going to be 0. Now what we are going to do is do a AND with the mask. So think of it this way. I have a number something like 1 1 0 0 1 1 and 0. 1 2 3 4 5 6 7 8. So this is just a number, okay? So as you can see, it ends with 0 and not 2 zeros, so it's not going to be a multiple of 4. If we do this operation, what happens? So our number is this, right? So it's going to be 1 1, and everything else is going to be 0. And if we do an AND, what we are going to get? Over here we're going to get 0. Over here we're going to get 1, and rest of the stuff are going to be 0 anyway, because everything else is 0. And we know that in terms of AND, if there's any 0, the answer is going to be 0. So then we do a return statement, over in which case we check whether the low bits are equal to 0. If they are equal to 0, it's going to return true. If they are not equal to 0, it's going to return false. So in this case, this one is not a 0, right? So it's going to return false. And if it was a 0, like this one was also 0, then it would have returned true. For example, another number 1 1 0 1 0 1 1 0 0. Now if we do the same operation in this case, what we are going to get is, if we do AND, we're going to get 0 0 0 0 0 0 0. In this case, the last two digits are zeros, in which case this low 2 bits is going to be equal to 0. So that, like this specific number, is multiple of 4. Another example we're going to look at is how to clear a number. So for example, this is how your normal binary representation is going to look like. For example, this is our number and we want to clear its sixth digit. Okay, so six digits. So we have this, and this is 1, 2, 3, 4, 5, 6. We want to clear this number. So how are we going to do that? What we are going to do is first create a mask and then shift it by 6, like shift 1 by 6. So at first 1 was here, then it was shifted by 6. So 1 2 3, sorry, 0 1 2 3 4 5 6. So it's over here. Then what we're going to do is complement it. So every single 0 is going to turn into 1, and this one is going to turn into a 0. Also um, I did a miscalculation. It's going to be 0 1 2 3 4 5 6. This is the number we want to clear. So anyway, over here you can see a 0. Now what we are going to do is do a X and mask. So what's going to do is, it doesn't matter what number was here, it's going to turn into a 0, and everything else is going to be the same as before. Because for example, in this case 1 and 1 is going to be 1, 0 and 1 is going to be 0, because equals to 0, right? In this case 1 1 is going to be 1. So nothing else changes, but in this case 0 is going to change, like clear this bit, and it's going to turn into 0. That's why clearing bit worked in this case. So another thing, like another example we're going to take a look at is how to print your bytes, like how to print the bits of a byte. So we know that every byte is basically a number of like 8 bits, right? This is what a byte looks like. So let's see what this function does. You're sending the byte as a parameter, and the first thing we're going to do is get a mask, and that mask is this hexadecimal number, which it looks like this. I hope that makes sense, because this one is 0 0 0 0 and this 8 means 1 0 1 0. So yeah, what we're going to do is run a for loop. It starts from 8, like we have integer 8. It stops when it's 0, and we are going to decrease it 1 by 1. What we're going to do is we are going to do a AND between the byte and the mask. So if this is your byte, the first thing that's going to happen is 0 1 0 0 1 0 1 0. It's going to AND itself with 1 0 0 0 0 0 0 0. So this is a 0, this is a 1, so it's going to be a 0, and everything else turns into a 0, right? So what it's going to print is it's going to print 0. In the next time, it's going to be something like this number, and instead of 1 being here, oops, um, nope, sorry, technical difficulties. So yeah, and then so it's going to print 0. Over here it's checking whether it's 0 or not. If it's 0, it's going to print 0. If it's not, it's going to print 1. Then we are checking whether bit is equal to 5. If it's 5, we're going to put a dash, because as you can see, I always put a dash over here. That's kind of like a convention, don't worry about it. And then we are going to shift by 1. Another thing to notice over here is we are doing shift by 1, right? But remember, mask is a uint, so that's why even though it started as 1 0 0 0 0 0 0 0 0, it's not going to pad itself with 1. Instead, it's going to make it 0 because it's an unsigned. If it was not unsigned, if it was just int 8, then it would have padded itself with 1. So anyway, then we are doing a right shift. In this case, the new mask is going to look like this. And in that case, when it does a AND with this one and this one is going to create a 1. And over here, this is going to turn into a false and it's going to print 1. So if you keep going like this, you are going to print the whole byte into bit format. Give it a try by yourself and it will make more sense to you. You can write this whole thing down by yourself. I'm just showing you 2 steps, but I hope that makes sense. If you don't get it, ask me during my office hours. So yeah, this is how the byte is going to look like. Like I said, because it's uint, it's not going to be padded by 1. Instead, it's going to be padded by 0. Another thing to check over here is byte and mask. It's going to equal to 0, like, sorry, byte and mask equals to kth bit of byte surrounded by zeros. So if it's 0, like I already showed the third phase, right? So if this one is not false, right? So in this case, it's not going to be equal to 0. So in this case, it's going to print 1 and so on. So yeah, if you want to turn a whole file into like bits, you can use this function and the previous one. So what it's going to do is the p current is going to start from the end. Now that's a very weird thing to do. So let's look at the parameters first. So you're going to read a file. So this is the file pointer. This is an array of the bits where you are going to put the bits one by one, and this is the length of the array. That's what these parameters mean. So p current is going to start at the end of the array. How do you think this points to the end of the array? Try to answer that to me. You have went through pointers and at least 2 assignments about pointers. If you still don't get it, you probably need to relearn pointer at this point. Get it? Anyway, my bad. So yeah, and this stuff, and this time we're going to start bit from the beginning. It's going to go through the whole thing like it's a normal for loop. At first, we're going to get the end of the like p current byte, and at the end we are going to go backwards. So it's kind of like this. This is the whole array. We're going to start from here, then go here, then go here, then go here, and so on. So we are doing a print byte. So what it's going to do is print the whole thing, and then if byte is less than length minus 1, print space. I hope that makes sense. So yeah, so what happens is, because we need to start from the end, why do we need to start from the end? What do you think that's the case? Like why we are starting from here? If you ask me, it's because remember this implementation of print byte. Let's see. In this case, we are getting the bytes one by one, right? So it's going to be something like this: 0 1 0 1. Think of it as a byte for now. 0 1 0 1 1 0 1 0. So we have, just imagine these four digits are bytes. These four digits are bytes. These four digits are bytes. So at first we are going to have a array like this, right? So we could start, we are starting from here. We're reading a byte over here, right? But then we are pointing over here. Then when we do a print byte, what it's basically going to do is put this byte over here. Then we're going to point here now. Do a print byte and it's going to point here. And then this one is going to point here. So yeah, that's what we're doing with the print bytes. Okay, so it's probably the final topic of this lecture. So integer divisions. So usually the division operator is a very costly one. Like for example, one of the sources indicate that executing an integer division instruction on an Intel Sandy Bridge CPU, that's a very old CPU, may require 29 clock cycles for 32-bit operands and 92 for 64-bit operands. So can you imagine how, like, what a big overhead that is? So if you could actually optimize it, your code is going to be very optimized, right? So let's see how you can do it. So one of the things you have already learned that if it's 2 to the power k, you can easily do a right shift and it's going to divide something by that. So for example, I have a number like this 1010, and then I have like 0101, and if I want to do something like divide it by 2 to the power 3, all I have to do is right shift it by 3. So this part is going to be thrown away and this part is going to be padded. So for example, in this case, this is 61, this whole number is 61, and I want to divide it by 8. So we know that 8 is 2 to the power 3. So if we want to do that, all we have to do is do n and shift it by 3, right shift it by 3. So this part is going to be thrown away, and this is the division, which is 7. Like it is shown over here. To get the divisor, what is it called? I forgot the English of it. I'm sorry. So quotient, I guess. Yeah, quotient. So if you want to get the quotient, it's going to be basically just like this, and everything else is just going to be thrown away. You can do it like this if you want, but this is just like too much work, and honestly it's not useful. And if you want the reminder of the division, all you have to do is get a mask. So the mask is basically going to be something like this. So what does it represent? So you need the last 3 digits, right? So this one's needs to be 1 and everything else needs to be 0, because if you do a AND, everything that has a 0 is going to turn into 0, so you can disregard the whole thing. This one is also 0, so this one is also going to turn into a 0. So all you have left is this part, which is the remainder. So by doing this, r equal to in and mask, then you actually get the remainder. So this is a very fast way you can do division, but it only works for 2 to the power k, and it won't work for something like 3 or 5 or 7 or something like that. It's only going to work for 2, 4, 8, 16, 32, and so on. So yeah, flip bytes. So this is just like a normal example. So I have if 0 0, I want to flip it, so I want to make it look like this. So what I'm doing here is I'm going to get high byte and going to shift it by 8. Remember, sorry, my bad. Okay, so I have a number. For example, maybe that number is something like this: AB CD. I want to turn it to something like CD AB. So I'm going to have a variable called high byte and going to do this. So what happens is, if I have AB CD and I do AND with if 0 0, if basically means 1 1 1 1, this is equivalent to f. So what's going to happen is this part is going to turn into 0, this is going to stay A and B. So high byte is basically holding on to this part. Then what I'm going to do is shift it by 8. Okay, so when you're working with hexadecimal, remember, if you want to shift this to this, you have to shift it by 8. Can you think of why that works? Think about it, like it's pretty easy. So yeah, so what we're going to do is do a right shift of high byte by 8. So this AB is going to be shifted here. Now I'm going to do in right shifted by 8. So this was n, right? This is going to be right shifted by 8. So the CD 0 0, and over here we have 0 0 AB. Then if we do OR, it's just going to be like this: CD 0 0 0 0 AB. We do a OR, it's going to turn into CD AB, what we wanted to turn it into. So this is how we are doing flip bytes. Add nibbles. We can also separate the nibbles by doing this. So we have the number itself, and what we're doing over here is doing an AND. This is a mask, right? And by doing a AND with that, we are getting the first nibble. Over here we're going to get the second nibble, third nibble, fourth nibble, and we want to sum them up. So this one stays wherever it is. By doing shift by 4, this nibble is going to be shifted here. In this case, it's going to be shifted here. In this case, it's going to be shifted here. So for example, I have a number something like A, B, C, D in hexadecimal, okay? So the first thing over here is going to happen is A, B, C, D. I'm ending it with 0 0 0 F. It's going to turn into 0 0 0 D. The next one is A, B, C, D and 0 0 F 0. This is going to be 0 0 C 0. Then I am doing a shift by 4. So it's going to be like 0 0 0 C. The next one is going to be 0 B 0 0, obviously. Shifting by 8, it's going to turn into 0 0 0 B. The last one is going to be 0 0 0 A. And then I'm just summing them up. So that's why this function works. And this one is zero odd nibbles. Well, I don't know, what does it do? At first we're just doing a mask, and we're honestly mean, I can explain, but like I don't know why this one actually matters. So anyway, doing and with this one, we have a number, for example, like 0 a b c. The first one is going to be 0 a b c, and we're going to do a and with 1. So c basically is what, a is, okay, I have to write them down. So 8 is 1000. 9 is 1001. A is 1010. B is 1011. C is 1 oops, my bad. 100. So yeah, we have this number, and if we do this, the first one is C, and this one is supposed to be ended with 1. So this one is not going to be, well, this one is going to be a 0. If it's a 0, n is going to stay the same, because it only works when it's not equal to 0. In this case, what's going to happen is this is 0 0. Okay, honestly, I don't know why this algorithm matters or what it's trying to do. I will make another video about it, to explain it better. But for now, yeah, that's all for this lecture. And honestly, this lecture is going to be helpful for your CO7 assignment. So, yeah, I hope this makes sense. If you don't understand, please post on Piazza, ask me in my office hour. Literally nobody shows up in the office hour. I don't know. Does nobody care? I don't know. But yeah, that's all. Thank you for listening.